So welcome to lecture number 5 on electrical circuits 1. So today we are going to discuss about network reduction techniques. So why we are going to study this network reduction techniques for electrical circuits? Because electrical circuit is a complicated circuits which will consisting of energy sources and passive elements. So to simplify the network, we have to use the network reduction techniques, and the network reduction techniques we are having series connection, parallel connection, series to parallel conversion, and parallel to series conversion, and voltage division and current division, and star to delta and delta to star transformation, and the voltage source to current source and current source to voltage source. Of course, the voltage source to current source and current source to voltage source we already discussed in the last lecture. So today we will see the remaining techniques. So the techniques, first we will start with the resistances are connected in series. So first we will discuss about the series connection, later we go for the parallel connection. So for series connection, if you can take, so the series means what? So the series means one end of the starting, for example, the resistance is having, so for example, if the resistance is having two terminals, one is starting terminal and another one is ending terminal. Similarly, if you can take another resistor, it is also two terminal element, it is having starting and another one ending. So if you can join the ending of first element to the starting of first element, so then we can say that these two elements are connected in series. Okay, so where we can use this series connection? So we can use this series connection in decorative lamp purpose. So decoration purpose. So for decorative lamps we can use this series connection. So for example, we can see that so here we are having, I am going to take two resistors that is connected in series, that is R1 and R2. So I am going to connect these two resistors to a voltage source. So now we have to find what is equivalent resistance of these two resistances. So to find equivalent resistance, first we will find what is the current flows into the circuit. So this is total voltage, this is a total current, and in series circuits we can see the current flows into the first element, I can take this as a I1, and the current flows into the second element, I can take this as a I2. So here we can, from the circuit we can see that the current flows into the series circuit, that is I1 is equals to I1 is equals to I2. That means in series circuits the current flows into all the elements will be the same. So but the voltages we can see here, so whenever the current flows into this resistors, the voltages will be, that is VR1, that is voltage across resistor 1 is equals to I1 into R1. Similarly, the voltage across R2 is equals to I2 into R2. So if you can take n number of resistors connected in series, then we can get, that is up to VRM, we can say that mth resistance, then the current flows to that mth resistance into that mth resistance. So if you can connect all these are in series, so we have to apply Kirchhoff voltage law here. So to find the equivalent resistance, so here V is equals to VR1 plus VR2 up to so on VRM, that is voltage across mth resistance. So let us take the if you can take like this, if you can take mth resistances are connected here, then it is VR1 plus VR2 plus up to VRM. So here what is this total V total V is nothing but I into total current into total resistance. So here I am going to take this expression here. So what is total voltage here? Oh, total voltage is nothing but total current into total resistance. So here in general we can say this V is equals to I into R. So I can take this as I into R. So here, so substitute this V and V1 and V2 and up to Vrm in this expression, then we are getting I is equals to I into R is equals to Vr1. What is Vr1 here? Vr1 is nothing but I1 R1 plus I2 R2 plus up to so on plus Im into Rm. So here in series resistor, in series connection, which one is same? Just now we said that current flows into that, all the elements will be the same. So let us take, I am taking that as I1 is equals to I2 is equals to up to so on, and Im is equals to I. So substitute this in the above equation, then we are getting as IR is equals to, so take I common here. So I1 is nothing but I here I am taking. So take I common. So then R1 plus R2 plus up to so on Rm. So take I cancel. So then R is equals to R1 plus R2 plus up to so on Rm. So this is the equivalent resistance in series circuits. So in series circuits, what we have to conclude is that the current flows into the series circuits will be the same, but voltage across the elements will be different. Now coming to the powers, we can see. So the powers will be supplied by the source is in any resistor circuit is equals to the sum of the powers in each resistor in series. So that is the sum source power is equals to, that is P1 plus P2 plus P3 up to P1. So that is here the total power supplied by the source is equals to the sum of the powers in the each resistors. Okay, so what is the power expression? So that is power P is equals to Vs is equals Vs into I, that is equals to total current flows into the circuit into total resistance. So that is, we can write in terms of voltage, that is Vs square divided by Rt. So this can be total power supplied by the source. So now coming to the resistors. So if you can coming to the parallel connection, resistances are connected in parallel. So now what is parallel connection? First we will see. So here if you can take m number of resistors here, so I am going to take m number of resistors. So that is R1, R2 and up to Rm. So if you can join all the starting points and if you can join all the ending points of that element, then we are getting parallel connection. So this is one point and this is one point. So we have to connect all the starting points at one point and all the ending points at one point. So then such networks we can call as parallel connection. So here in parallel connection, if you can apply the voltage, supply voltage to this parallel combination of these elements, then what happens here we will see. So here the current flows into these branches. Here we are having m number of resistors are connected in parallel. So each branch current we can assign as I1, I2 and I3 and I up to Im. So what I am going to tell here is that, so the current is divides into the parallel circuits. That is, current is not same in parallel circuit. Okay, so current is divides into the parallel circuit based upon the depending upon the resistance value. So if the resistance is very less, then high current will flows. If the resistance is very high, then low current will flows into that branch. So the best example for the parallel connections is the household appliances. So whatever the loads we have connected, all the loads are connected in parallel. So here one more point we have to take here, that so the voltage at every branch, we can see if we can take this, the voltage at this point and voltage at this point and voltage at this point and up to voltage at this point here. So we can say that the voltage across all the points will be the same because it is connected to positive terminal and it is connected to negative terminal. So that means we can say that the voltages in parallel circuit will be the same. So voltage in parallel circuits will be the same, but current will be divided. Now let us find the equivalent resistance of this circuit. So for finding the equivalent resistance of this circuit, so we can take the expression, that is current I is equals to IT plus I1 plus I2 up to IM. So what is the total current here? So the total current IT is equals to total voltage divided by total resistance, or we can sum R equivalent also. So what is I1 here? According to Ohm's law, current I1 is equals to V divided by R1. So this is R1. So this is, or we can write V1 divided by, so voltage at this node V1, V2, V3. Okay. So V1 divided by R1. Similarly, the current flows to the second branch, that is V2 divided by R3. Similarly up to so on. So IM is equals to the current flows to the, that is VM divided by RM. So this is according to Ohm's law. So current I1, if you can substitute this total current IT and I1 and I2 up to IM in this expression, then we are getting as, that is V divided by RT or R equivalent, I am right. So R equivalent V1 divided by R1 plus V2 divided by R2 plus up to so on VM divided by RM. So that means here if you can take V common, why? Because in parallel circuits voltage is same, that is V1 is equals to V2 is equals to up to so on VM, so which is nothing but V. So if you can take the voltage common, so then that is V divided by R equivalent is equals to, if you can take V common here, 1 by R1 plus 1 by R2 plus so on plus 1 divided by R equivalent. So if you can take V, we cancel, therefore 1 by R equivalent is equals to 1 by R1 plus 1 by R2 plus so on plus 1 by RM plus 1 by RM. So this is the general expression for equivalent resistance in parallel circuits. So for example, if two resistors are connected in parallel, then what is the equivalent resistor, that we will see now. So if you can connect the two resistors are in parallel, that is R1 and R2, so then what is the equivalent resistance of this circuit? So that means 1 by R equivalent is equals to 1 by R1 plus 1 by R2. So to simplify this one, we are getting R equivalent is equals to R1 R2 divided by R1 plus R2. This is the equivalent resistance when two resistors are connected in parallel. So now we can see the powers also. So this is the expression we have already seen. So power in parallel circuit is given by, so here also the power, total power supplied by the source in parallel circuit is equals to the sum of powers in each resistor in parallel. So that is, so PS, that is source power, is equals to sum of individual powers, that is P1 plus P2 plus P3 up to so on PM. So where M is nothing but number of resistors are connected in parallel, and PS is nothing but total power, PM is nothing but mth power in the last resistor. So these are the resistors connected in series and parallel. So now we move on to the next topic, that is voltage division rule. So voltage division rule means here in series circuits we have the voltage may not be same, so the voltage will be divides. So based on the current flows to this one, current flows into this resistor, the voltage will be drops across this one. So the voltage may not be equal in the resistors. So we have to find the what is the voltage drop across particular that resistance. Then we can go for the voltage division rule. Okay. So for example, here in case we can see if m number of resistors are connected in series, then what is the voltage division across this resistance and this resistance, this resistance. So that we will find now. So for that we can see the total current flows into the circuit, that is current I is equals to V divided by R1 plus R2 plus up to R1 up to Rm. So the voltage across the resistor is nothing but the current passing through it. So whatever the voltage is there, we can say here the voltage across the resistor. If we can say the current pass through this resistor, then we can see this voltage across this resistor. So we can say that if for example in the circuit, if you can see what VR1 and VR2 and up to VRM, so then VR1 is equals to I into R1, VR2 is equals to I into R2, and VR3 is equals to I into R3 up to we can see VRM is equals to I into Rm, because in series circuits current is same, so that's why I is common here. So then finally we can write in place, we can substitute in place of I, so this total current, so that is current I is equals to Vs divided by R1 plus R2 plus up to so on Rm into Rm. So from this equation what we have to conclude is that, so that is general expression for this one is the voltage across mth branch. Voltage across mth branch is nothing but total voltage, that is our source voltage we can say. So this is source voltage, okay, multiplied by that resistance, that branch resistance divided by sum of the resistances. So the general expression you can see here. So for example, this is the voltage at particular branch, m is nothing but mth branch, and this is the mth resistance divided by total resistance. This is the source voltage. So in general I can write as, so voltage across any branch we can say, that is voltage across mth branch we can say, that is Vm is equals to total voltage or source voltage into the multiplication of that resistance divided by sum of the resistances or total resistances. So now let us see one simple example here. So we can take the two resistors are connected in series. So if you can find the what is V1 and what is V2 and what is, these are the R1 and R2, and this is the total voltage or source voltage were applied here. So that is Vs is equals to, so Vs we are applied here, that is source voltage. So according to voltage division rule, so the formula is the voltage across first branch, that is V1 is equals to total voltage, that is source voltage, into that resistance divided by sum of the resistances. So this is the voltage division rule. According to voltage division rule, we can find the voltage across that branch. Similarly, if you can find the voltage at second branch, that is V2 is equals to total voltage into that branch resistance divided by sum of the resistances. So this is about the voltage division rule. Next, coming to the current division rule. So current division means it is possible only in case of a parallel circuits. So in parallel circuit, current is divides and voltage will be the same. So we have to derive the, so what is the branch current, that is I1 and I2. Let us see now. So according to the current division rule, so first we can write the expressions for current flows into the each and every branch. So that is I1 and I2. So I1 is equals to Vs by R1 and I2 is equals to Vs by R2. So where RT is nothing but the total resistance. So that is given by R1 R2 divided by R1 plus R2. So what is the total current now? So total current IT is equals to Vs divided by RT. So Vs divided by what is RT? That is total resistance. So that is R1 R2 divided R1 R2 into R1 plus R2. So from this expression we can write as IT is equals to I1 into R1. So what is I1 into R1? I1 into R1 we can came from this expression, that is Vs is equals to I1 into R1. So I can substitute in place of Vs, I can substitute V1 and I in place of I1 and R1 divided by R1 R2 into R1 plus R2. So from this I can write that expression for I1, that is I1 is equals to total current into, so here R1 gets cancelled here. So R2 divided by R1 plus R2. So this is the expression you can see. Similarly, we can see for the second one also. So that is I2 is equals to IT into R1 divided by R1 plus R2. So the general expression we can see here. So that is the current flows into mth branch. We can take that as total current into opposite resistance. You can say that opposite resistance divided by sum of the resistances, divided by sum of the resistances. This is the general expression for current division rule. So let us find the current division rule for two resistors. Two resistors are connected in parallel. So this is the total current is flows into the circuit here. So this is I1 and this is I2. So this is total current. So this is R1 and R2. So then what is the current flows into the first branch? So according to the definition, so that is total current into opposite resistance, means the current flows into this opposite branch. So that is opposite resistance divided by the sum of the resistances, that is R1 plus R2. Similarly, if we can take for second branch, so that is total current into opposite resistance for this branch. It is opposite is R1 divided by R1 plus R2. So this is the current division rule. So this can be used in parallel circuits. Now next technique that we are going to see, that is delta to star and star to delta transformation. So for simplification purpose, this technique is also very useful. So now let us derive the conversion from delta to star and star to delta conversion. So here for converting from delta to star, so we have to consider these are the three diagrams here. So first I am taking the delta connections. So delta connections means here we can see this type of networks we can see in the three-phase circuits. So for the simplification, okay. So here how to form a delta and how to form a star here, so that we will see now. So here I am going to take the three resistors here. So each are having the starting and ending points. So to form a delta, so the ending of the first one is connected to starting of the second element. Similarly, ending of the second element is connected to the starting of third element. Then ending of this third element is again connected to this starting of this one. So this is the connection. So then it is formed as a delta. So then we can also call this delta, we can also represent in pi shape also. So that means here we can represent in pi shape also. We can represent in pi model also. This delta is can represent in pi model also, because it is in the closed nature. Similarly, if you can see for the star connection, so the star connection, again I'm going to take the 3 resistors. So each are having starting and ending points, each starting and ending resistance, starting point and ending point. So if you can join all the starting points at one point, or if you can join all the ending points at one point, then you will become as one neutral point you are getting here. So that means here, so for example, if I am joining all the ending points at one point, so all the starting points from this we can give in the supply, or we can take the supply here. So then it is forms as a equivalent, and this forms as a star connection. So the star connection is also called as Y connection. So this delta connection, it is an enclosed loop, it is an open circuit. Okay, so now let us derive the conversion from delta to star. So here first we have to see the delta connection here. So first we have to see that between the impedance between these 2 points, when we can transform from star to delta and delta to star, must be the same. So that's why first we have to see that the RAB, you can see here RAB in delta connection. So this is RAB is equals to, so I am writing here, so this is RAB, this is A and this is B, see this is R1. So in between 2 points we are having R1, and so here 2 resistors are there. So you can see on the diagram here. So R2 and R3 are connected in series. So that means in between these 2 points R2 is there, and so R2 and R3. So this is R2 and this is R3 is there. So these 2 are connected in series with respect to these 2 points. So R2 and R3 are connected in series. So therefore, so R1 is equals to, so therefore RAB is equals to R1 parallel with R2 plus R3. So this is the expression we are getting between the 2 points A and B. So similarly, if you can see the star connection also. So in the star connection, so what is the equivalent resistance between these 2 points means, so anyway it is in open circuited, so we are not considering here. So we have to consider only these 2 resistors. So that is in star connection, the RAB is equals to RA plus RB. So this expression in delta connection, then this expression will be in star connection. So from this, what we need to conclude that the impedances of the 2 points between A and B in delta and in star connection must be equal. So since 2 systems are identical here, so the resistance measured in between the 2 terminals must be equal. So therefore we have to equate these 2 points here. So then we are getting as RAB is equals to R1 of R2 R3 divided by R1 plus R2 plus R3. So this is the expression 1 for considering A and B terminals. Similarly, if you can considering the BC and CA terminals, then we are getting the second expression, and also we are getting the third expression. So if you can add all these 3 equations, then we are getting the fourth equation. You can see this is the fourth expression we are getting here. So if we can subtract the equations 1, 2, 3 from equation number 4, then we are getting RA, RB and RC. So here from this equation we have to subtract equation 1, 2, 3 and 4. Then we are getting the values of RA, RB and RC, that is equivalent star connection. We are getting RA, RB and RC values. So that is RA, RB and RC we are getting from delta to star connection. So this is the expression we are getting here. So how to remember this expression while converting from delta to star? So all of you see the diagram here. So to convert from delta to star, so first we require RA. So what is RA? So RA is equals to, we can say this as R1, R2, that is, we can write here. So for example, these 2 resistors are touching at the point A. So that is R1, R3 divided by sum of the resistances. R1, R2 divided by sum of the resistance. Now let us verify that one. We will see. So what is RA here? RA is equals to R1, R3 divided by R1 plus R2 plus R3. Similarly, we can see for RB also. So RB is equals to, so this point B in delta connection, it is touches the 2 resistances here. So that is RB is equals to, I can write here as R1 R2 divided by R1 plus R2 plus R3. Similarly, RC we can write as this point C. So from this point C we can see two resistors are connected to point C here. So then R2 R3 divided by R1 plus R2 plus R3. So this is the conversion from delta to star. So for example, if you can take, if all the values of the delta connections are equal, so let us take this is R1 is equals to R and R2 is equals to R and R3 is equals to R, then what is equivalent star connection? So now let us see if we can substitute R1 and R2 and R3 values. So then we are getting as R1 square divided by 3R. So RR will get cancelled, then we are getting the R by 3. So while converting the delta connection to star connection of equivalent values of resistance, then we are getting the resultant value as R by 3 times. Okay, so this is the conversion from delta to star. Similarly, if you can see for the star to delta conversion. So for star to delta conversion, simply we have to do here, we have to multiply the equations 4, 6 and 6, 7 and 7, 5. So we have to multiply this expression. So the expressions we can see here. So we have to multiply 5, 6. So 5 is there. So 5, 6, 6, 7 and 7, 5. We have to multiply this expression. So then we are getting the result. This is the result we are getting. So after that, we are getting the expression 8 here. So if you have to divide this equation 8 by equations 5, 6 and 7, then we are getting the corresponding delta values of R1, R2 and R3. So these are the corresponding delta values of R1, R2 and R3. So coming to the formula here, how to remember the formula for star to, so conversion from star to delta, how to remember the formula here. So first to find the R1 here, so to find the R1, to convert from star to delta. So let us see the formula here. So that is R1 is equals to RA plus RB plus RC R divided by RB. So you can cancel this one. So then you are getting as R1 is nothing but RA plus RC plus RA RC divided by RB. This RB. So like that we can see here. So that is this RB is connected here. So to find R1, so to find R1, that is I am connect this R1 here. So between these 2 points, this is R1 here. So then R1 is nothing but RA plus RB plus RA RB divided by RC. Similarly, if you can connect delta, if you can connect this resistance here, that is R2. So R2 is equals to RB plus RC plus RB RC divided by RA. Similarly, to convert from star to delta, that is R3. So the R3 formula is R3 is equals to RC plus RA plus RC RA divided by RB. So if you can take all the equal values of that star connection, let us take RA is equals to R and RB is equals to R and RC is equals to R, then what is equivalent to delta we will see. So then equivalent delta means that is R1. So if you can substitute all the values are equal, that is R square divided by R. So then we are getting as the resultant is 3R. So that means here for conversion from star to delta of equal values of star connection, then we are getting the 3R. Resultant value we are getting as 3R. So this is the conversion from delta to star and star to delta. Okay. So thank you for listening. So that's all. Thank you.